Now we will take a look at the reactions of esters. We have talked about many of these reactions on the list here. The first one we will review is the reduction of ester to alcohols. Esters can be reduced by lithium aluminum hydride, LAH, to a primary alcohol and an alcohol that the ester linkage is attached to. For this reaction, sodium borohydride won't work because it's weak. It cannot react with the less reactive carbonyl group. One thing I do want to mention here is, in the reduction reaction, the carbon being reduced is the carbonyl carbon. At the same time, the ester linkage will be cleaved, and the R prime here is not reduced. It's just being cleaved as another alcohol. All right? So let's take a look at example when we have a cyclic ester. What will be the product when this cyclic ester is reduced by LAH? Remember, the ester linkage is cleaved. So you are going to get one alcohol from this R prime part. And the carbonyl carbon will be reduced to an alcohol. So in the product, you should have two hydroxy functional group. Here is the product. So again, carbon 1 is reduced from a carbonyl to a primary alcohol. Carbon 4OH is just the hydroxy group that was in the ester linkage. It's being cleaved. It's not reduced. All right. So one more time, for reduction of ester, two alcohols will be produced. One of them is the reduction product. The other is just from the cleavage of the ester. All right. The next reduction is the reduction of ester to aldehydes. Actually, esters and acyl chlorides both can be reduced to aldehydes by a relatively weak reducing agent, dibol. Dibol stands for diisobutyl aluminum hydride. It's based on aluminum hydride, but it's modified so that it cannot reduce aldehyde further. The third reaction is the reaction of esters with Grignard reagent. This reaction will provide tertiary alcohols as the final product. So the first equivalent of Grignard react with ester, it gives a ketone intermediate. And because ketone is more reactive, so it's going to react one more time with Grignard reagent to get the tertiary alcohol. So two equivalent of Grignard reagent is needed here when the ester is the starting material. Again, you cannot stop the reaction at the ketone stage because ketone is more reactive than ester toward the Grignard reagent, the nucleophilic addition reaction. All right, let's see the next reaction. Suppose we have two equivalent of a Grignard and we have an ester. Can you give the product for this reaction? Remember, the product will have an alcohol functional group. And the carbon the OH is attached to will have two identical alkyl groups. Both of them are from the Grignard reagent. So here is the product. Two phenyl groups will be attached to the carbon where the OH is. All right? Next reaction. This is one of the most important reactions for esters. Hydrolysis. Hydrolysis of ester will give carboxylic acids and alcohols back. Hydrolysis of ester can take place either under acidic condition or basic condition. So we will look at them one at a time. First, let's see acidic condition. Under acidic condition, hydrolysis of ester provides carboxylic acids and alcohols. This is the exact reverse reaction of Fischer esterification, right? Fischer esterification is also under acidic condition. Carboxylic acid and alcohols gives esters, right? So this reaction is under equilibrium. It favors the ester slightly, but it's not going to give you 100% yield of either ester or the hydrolysis product. In order to increase yield of the product we want, we have to find a way to add more reagent or remove some of the product based on Le Chatelier's principle. For example, if we want to hydrolyze an ester, you are going to add more water. Use excess water so that the concentration of water becomes higher and it will shift the equilibrium to the right-hand side, to the carboxylic acid and alcohol side. On the other hand, if you want to do the reverse reaction, the Fischer esterification, you want to remove water from the system, which means we can use distillation to get rid of the water being removed from the system. Then it will drive the reaction to the left side, to the formation of ester. All right. Let's take a look at the mechanism for hydrolysis of ester. Even though it's exactly the same reverse step for Fischer esterification, I do want to go over it one more time. Under acidic condition, the carbonyl oxygen will be protonated first. So it will give a positive charge on the oxygen, and the carbon will help to share that positive charge. So protonation activates the carbonyl carbon toward the nucleophilic addition. The second step is the nucleophilic addition. Water is the nucleophile to attack on the carbonyl carbon, breaking the CO double bond. And the product is a tetrahedron intermediate. A quick deprotonation on the oxygen at the bottom gives the neutral tetrahedron intermediate. Then there will be another protonation step on the OR group. Then, when the electrons on the oxygen of one of the OH to come back to reform the carbonyl group, alcohol will be the leaving group. And the last step is a deprotonation that gives carboxylic acid. All right. So again, this is exact the reverse reaction of Fischer esterification. If you go from the last step to the first, that's the mechanism for Fischer esterification. And no matter if it's esterification or hydrolysis of esters, the reaction is classified as nucleophilic acyl substitution. The first stage in the nucleophilic acyl substitution is the formation of the tetrahedron intermediate. And the second stage, the tetrahedron intermediate collapses or dissociates to give the product. And you should be able to determine which group will be the leaving group when this dissociates takes place. All right, so now let's move on to the basic condition. The difference between acidic and the basic condition, one of the major differences is that basic condition, the reaction is irreversible. So hydrolysis of ester under basic condition, it gives carboxylate ion and alcohol. And the carboxylate ion after acidification will provide carboxylic acid. The basic hydrolysis of esters is also called sabonification. Sabonification means soap making. So why we call it soap making? So in ancient times, people use this hydrolysis of ester under basic condition to make soap. How? Remember just now we talked about fats and oils are esters. So in ancient times, people will hydrolyze animal fats with wood ash, which contains sodium bicarbonate, a base, to make glycerol as well as fatty acids anion, which are carboxylates. And if you remember from the last chapter, we talked about micelles, right? Micelles are long-chain fatty acid anions that tend to form micelles, right? So when the animal fats are hydrolyzed under basic condition, one of the products is the carboxylate of the fatty acids. So they tend to form micelles, which can be used for cleaning. They can be used as soap, right? So the hydrolysis of ester under basic condition can make soap, and the reaction is also called sabonification reaction. Now let's take a look at the mechanism. The first step of the mechanism, hydroxide as a nucleophile attacking on the carbonyl carbon of the ester. This is quite similar to the acidic or basic condition for the hydrate of aldehydes that we've mentioned before. Under acidic condition, protonation takes place and the carbonyl is activated so that the carbonyl can react with a weaker nucleophile, the neutral water molecule. Under basic condition, we have a stronger nucleophile, hydroxide. So the hydroxide will react with the carbonyl directly. We don't need to activate the carbonyl carbon. So this is the nucleophilic addition, which will provide the tetrahedron intermediate. Now we have a negative charge on one of the oxygen, which can come back to reform the carbonyl. At the same time, the alkoxide will serve as the leaving group. So after this step, we get one carboxylic acid and one alkoxide ion. Alkoxide is the conjugate base of alcohol, right? And we've learned that alcohols are weaker acid than carboxylic acid. So now we have a stronger acid, carboxylic acid, and the stronger base, the alkoxide of a weaker acid. So a quick acid-base reaction will take place. Alkoxide will grab the proton from the carboxylic acid. The final product will be carboxylate, the conjugate base of the carboxylic acid and alcohol. So in this three-step mechanism, the first two are still under equilibrium, which means they are reversible. But the last one, the acid-base reaction, is irreversible. That's the step that drives whole reaction forward. That makes the whole reaction irreversible. So, as a result, if you want to hydrolyze an ester, you probably want to choose basic condition if possible, because it will make the reaction go to completion. All right. The next reaction we will look at is the reaction of ester with ammonia or amines to make amides. So again, regarding the reactivity or the stability of the acyl substitution, we have acyl chloride, acid and hydride, and then esters. The last one is amide. So esters can be used to make the compound after it. Esters is more reactive than amide, so we can use esters to make amide. The examples shown here, esters reacting with ammonia, NH3, is going to provide an amide, and the alcohol will be the leaving group. If we react an ester with an amine, we can provide substituted amide. Okay, these are the same type of reactions. We will talk more about this reaction when we get to the amide part. It's the same nucleophilic acyl substitution. It goes through the tetrahedron intermediate. All right. And the methyl and the ethyl esters are more reactive to make amides. All right, some questions for you to think about. If we have this tetrahedron intermediate, can you tell me what reaction we are doing here that we have this tetrahedron intermediate? Or put it in another word, if this tetrahedron intermediate is formed, what product will it give? We've had similar questions before when we talk about the nucleophilic acyl substitution. And lastly, we have this reaction here. One is an ester with an amino substituent. The other in the product is an amide with a hydroxy substituent. So the reaction goes from the ester to the amide. almost automatically. Can you propose a mechanism to explain these results? Why the reaction favors the product side, the amide, and what kind of tetrahedron intermediate do we have here? All right,